Welcome to this tutorial where we will process the beta-galactosidase data that we have in the Scipion tutorial section in the web page. So this is the general aspect of Scipion once you have finished your analysis. So here you have the different operations that you can perform. They are distributed in different categories. So for instance, for estimating the CTF of a set of micrographs, you have different options, and when you click at one of the options, what you have is a form where it is asking for if you are estimating the CTF, which are the micrographs that you will use, which is the downsampling factor just for the estimation of the CTF, and different parameters particular to that algorithm. So once you have filled them, you execute the protocol, and a new box like these ones here will appear in the part of Scipion where it shows what you have actually done. So here we have the full workflow, and in this workflow we have different parts. We have used labels. You see, if you click here you can add labels. We have created a few labels, some of them related to the micrograph processing, particle processing, 2D classification, etc. So we have some of the boxes are related to the processing of micrographs. Then these ones are related to the particle picking. Then these ones are related to 2D particle classification and pruning. So choosing which are the particles that better represent your structure. Then we have constructed here an initial volume, and this initial volume has been used for doing a 3D pruning, so some 3D classification that rejects particles that do not really look like particles. And once we have an homogeneous population of particles, we go for a refinement of the 3D structure that we have calculated before. And finally, we will validate our structure. So in this tutorial, we will show only in this video tutorial, we will show only the first part, and the following parts will be recorded in separated videos. Okay, so the first thing you have to do in Scipion is to let the system know that you have some movies. So for instance, we run this protocol, import movies. This is where the movies were, and the directory where they were, and from that directory we are taking all the files with the extension MRCS. And then we are asked about the voltage of the microscope at that point, of that microscope, what is the spherical aberration, and some other parameters related to the acquisition, like the sampling rate. We can also give dose in electrons per angstrom squared. We can also give gain and dark images for the cameras. So once you execute this, what you will have is a summary of what you have done. So here you have a summary of the input and output. So we have only, in this import, we have only an output object, and a short summary of what has been done. And if you click on analyze results on any box, on any protocol, you will have an analysis of what that protocol has done. So this one is importing movies. So what we have is a list of the movies, each movie with the sampling rate associated to it. And the first thing we should do is to verify that the gain has been correctly handled. So for that we have one of the protocols that is here, movie gain. So you would be asked which are the movies that you want to estimate. So at that point would be only the import movies. Then you would select them, use the existing gain image, yes or no, depending on whether you have imported with an already with. So if you import non-gain corrected images, you may import the gain to correct them on the fly. and otherwise it is assumed that the images have been corrected for the gain, as this was the case in this example. So this movie gain would verify that the gain that was applied was correctly done. So this is the gain estimated for one of the movies. So you can see that the mean value, that should be 1, is already 1. The standard deviation around 1 is relatively small. The minimum and maximum gain, they are also very well centered about 1. So this means that this this set of movies have been correctly corrected for the gain. We can also see at the gain image. So if we look at the gain image, we see some pattern. These patterns are normal from the residual gains. So once you correct for the gain, for the true gain of the camera, what you have is a residual gain. So this residual gain should be always around 1. This is what we have been verifying before in this summary. We can also see that through the histogram of that image. So we can analyze the histogram, and we see that it's very much centered about 1, and it goes from 0.99 to 1.00. So this is a good gain. Good. So the gain was good. Now we go to align the frames so that we correct for the beam induced movement. So here we have used the correlation alignment in XMIN, and before that we can verify what are the parameters to run this. So the set of movies that you want to align, which are the frames that you want to align. So these movies had 16 frames, and we are aligning from 1 to 16. You may skip, some people skip the first 1, 2, depending on whether they expect that the beam induced movement of the first 1 or 2 or the first few frames is larger than the rest. And also you may use all of the frames to produce an output image or not. You can do some binning here. This binning is actually performed in Fourier space, so it is not a binning by itself, but it is a downsampling. And then you can also do a filtering while to estimate the shifts between one frame and the next. You need to perform some correlations. These correlations are better defined if you remove noise, and the noise that we are removing is everything that is above 4 angstroms, so very fine details of the image that we normally don't care about. Okay, so once you run it, you would have an output like this one. So this one is this movie has been estimated to shift like this. So this would be the first frame. The first frame is at location 0, 0. So from the first frame to the second, there is a very small movement. You can see the axis. This axis is about 0.1, and in Y it is moving much less. So it is 0.1 in X, 0.005 in Y. So this would be from frame 1 to frame 2, from frame 2 to frame 3, and this would be the pattern, the path that these frames have been going under the microscope. So nearly no movement. That is why also this power spectrum looks the same. So normally the left power spectrum represents the power spectrum before correcting for the movement, and the right one is after correcting for the movement, and they look the same because there was almost no movement. If there is some significant movement, then you see that the two power spectra look different. So one has fainting rings, while the other one has stronger rings. Okay, so we can verify for a few of them. So for instance, let's open this one. So this trend of very small movement is also confirmed by most micrographs here. Good. So we have checked that there is almost no movement. and if there was some significant movement, we have corrected for it. This is a global alignment of the movement, and one advantage of this correlation alignment in XMIP is that it is relatively robust to errors, estimation errors of the frame movement, and it doesn't affect so much the final output. And due to the very low signal to noise ratio that we have in the frames, these errors are relatively common, so this is something you should worry about. So once you have corrected for the global movements, you should correct for the local movements. So this optical flow alignment should be taking a globally corrected movie, and again you are asked from which frames to which frames you want to do the alignment, and normally you don't have to touch any one of the default parameters. They make sense. This algorithm is implemented in GPU, also in CPU, and you can apply the dose filter here. So if you know the dose that have been applied to your frames, then you can correct for those for the dose here. So at the end, what you have is something like this. So you have, again, left part is the uncorrected image, the right part the corrected image. So again, this in this case they don't move so much, so that is why they look the same. And if you look at the plot of drifts, you see from frame 0 to frame 1 there was very little drift. From frame 1 to frame 2, very little drift, about 0.05 pixels. And remember that this is local movement, so each location may move independently from the rest with some regularization, but so that means relatively smooth movements, but they can move in different directions. So what we are representing here is this average of the absolute value of the movement. So that means that on average every pixel from the first frame to the second move about 0.1 on average, and we don't care about the direction. That is why it looks like an ever growing curve, because we are adding absolute values. Okay, so we may look for some other movie just to see if the little movement is still confirmed. So we see that locally there was also very little movement. If there was a micrograph with very large movement, we may delete it at this point. So let's say that we want all micrographs except the first one, so we would click on the second micrograph, right click, select from here, and then invert the selection. This one we disable, so we have disabled the ones before number 2, that there is only one, and then we can create a new set of micrographs. And this new set of micrographs, instead of having 15 images, 50 micrographs, it has only 14, because we have rejected one because it had very large movements. But this was not the case, so we will not do it now. Okay, so we imported the micrographs, we verified that the gain was correct, we have corrected for the global alignment, we have corrected for the local alignment, and at this point we didn't look at the micrographs, but so we analyze results again, and if we open, sorry, I opened twice, actually 3 times. So if we open the micrographs, right click on the micrograph name, we can see that it looks as a micrograph. This is also something that we should verify, that there have been no big mistake, so that the micrographs become empty or corrupted with totally nonsense. So it looks like particles on the eyes. Here you see the carbon edge, and we see that the particles are black particles. We can zoom in with the shift and the wheel of the mouse. So we have we have black particles over a brighter background. So the background is the eyes, so we have black particles on white eyes. And some algorithms don't care, but some other do care about this. So the standard assumption is that we have white particles instead of black particles. So the next step that we will do is to pre-process our micrographs to invert the contrast. So you can see that we have taken the micrographs produced by the optical flow alignment, and then we invert the contrast, and the output we should see that these micrographs now have white particles over a dark eyes. So with these micrographs now, we go into the CTF estimation of the micrograph. So the CTF is how the main parameter is the defocus of the microscope. So when the micrograph was taken, the microscope was defocused by a certain amount. So we have to estimate this certain amount. There are some other parameters that define the envelope. We will see it later. So for doing that, we can go to the CTF estimation part. We have here, for instance, CTF find. So we have already run it. So we have here the form that we used. So these are our micrographs. Here we can, just for the estimation of the CTF, we can downsample the micrographs, and the effect of that is nicely shown in here. So this is our list of micrographs. This is a representation of one of the micrographs, the one that is selected, and for this micrograph we can compute the power spectrum. So the power spectrum, we see that we can see the tone rings, and they nicely occupy most of the Fourier space. So this is the Fourier space, and it is normalized to go between -0.5 to 0.5, and we see that the tone rings are not very much concentrated at the origin. So if this was the case, that means that the sampling rate is too high for the information content that we have in the micrograph. So these are very tiny tone rings are difficult to see by the algorithm. So it is better if we do a downsampling. Just for the illustration, we will see how it changes if we increase the downsampling factor. We can use any continuous, any real factor here. So now the tone rings become larger because we are focusing more at the origin of the original micrograph. So we can go back to our downsampling of 1, so that means the same sampling rate as the original data, and then we can choose the area in which the tone rings have to be found. So with these controls here, we are saying that the tone rings should be looked in this blue shadowed area. And once we are happy with these parameters, you may verify that they are fine also for other micrographs, and once you are happy, you would select them, and these parameters are copied to the form. We will not do this now because we don't want to spoil what we have already done, but if we were running this protocol from scratch, then we would press on select. Here I will press cancel, and we will keep the parameters that were used when the protocol was run. Okay, so now the CTF looks like this. So this is the power spectrum seen experimentally, and this is the simulated power spectrum. So the main parameter of the power of the CTF is the defocus. Once you choose the defocus, automatically it produces some tone rings in the Fourier space. And what we should see here is that the rings predicted by this defoci are the same as the rings that we experimentally observe. And we clearly see that this is the case for most of the micrographs here. We can also sort by different parameters. So for instance, we can sort by defocus. This defocus is measured in angstroms, so this is 1.9 microns in defocus. So this is the smallest defocus that we have used in this data set. The largest one was 3.4 microns, so they are reasonably good. Sometimes you see that the algorithm fails to estimate the power spectrum, so at that point what you can do is right click on the failed spectrum, so and say recalculate. So now in this recalculate you would supply the first, so this blue area where the tone rings should be looked for, so it would be something like this, and then you can draw with the left mouse button, you can draw the first 0. So if you can see, every time you draw the 0, you are given in the image J toolbar, you are given which is the estimated defocus for this image. So this would be about 3.4 microns. That is exactly or about the value that we have seen that was estimated by the algorithm, because in this case it was correct. So all of them are fine. So if there is some micrograph that you think it is not correct, you can also deselect it. So you disable this one, you disable this one because you don't like the CTF of these ones, and then you produce a new set of micrographs. But again, this is not our case. In this case, all micrographs were good. You can also inspect the CTF resolution. So the CTF resolution is a parameter estimated by CTF find 4 that tells you which is the estimated maximum resolution that you would reach with this micrograph. So with this micrograph, it is expected that you could reach 5.6 angstroms. There is some drawback or catch in these values. If you look at the sampling rate is 3.5. So that means that Nyquist frequency, this is the maximum achievable frequency that you can have in your micrograph, is 7. So just by definition of sampling, this estimation of 5 angstroms that we had, so we had here 5 angstroms in here, so this 5 angstroms is an overestimation. And also, so Nyquist, this point here is 7 angstroms, and we cannot have 5 in our data. So there is also some overestimation here, and it is because CTF find is very good and very fast in estimating the defocus, but it is not estimating the envelope. So you see that these tone rings are fading. So this fading means that at some point, at some frequency, we don't have any structural information anymore. So the maximum frequency is limited not only by the focus but also by the envelope. So now we will use XMIN that is estimating the envelope, and we can see how we used XMIN. So these are the micrographs that we want to estimate, and there is an interesting feature by Scipion, that is that you can reuse the CTF estimate of some algorithm as the initial point for some other algorithm. So for instance, we have estimated the focus with CTF find, and we can provide this input as the initial point for the CTF estimate of XMIN. And the results are these. So we see that for many micrographs we have a correctly estimated CTF, so we have the same tone rings as before, and also now we can see how the tone rings are fading in a space, so that in frequency space, so that there is a maximum frequency below which we cannot see any other structural information. This frequency here is estimated by XMIN, it is this point. It is the frequency at which the envelope drops below 1/100th of the maximum value. So at this frequency, 7.6, the envelope has multiplied or has divided the extraction information by 1/100th. So this is quite a lot of reduction of amplitude, and probably beyond this point you will not be able to recover more extraction information. So we can see that our maximum resolution, it is estimated to be about 8 point something angstroms. And here we also have some other criteria to evaluate whether the micrographs are good or not. So for instance, we have the CTF margin. So the CTF margin is an estimate of how strong are the tone rings with respect to the noise. So for instance, here we have a micrograph at which we can only see the first ring. The second ring cannot be seen. So the margin there is very low, while for the rest of micrographs the margin is relatively large. And we can also estimate what is the defocus ratio. So the defocus ratio is the ratio between the two defocus. So that is one defocus in one direction, another defocus in the other direction. Both of them are very similar, and the ratio between these two is 1.0003. So they're almost the same. So you can check on this defocus ratio and put a threshold of your own. So let's say you wouldn't like this ratio to be larger than 5%, and so you remove all those micrographs that has a ratio larger than that. This astigmatism can also be seen in here. So if we look at the columns, there are some other criteria. That is, for instance, all these CTF crit, they are criteria of quality criteria of the CTF. So we can verify this one, we can verify this one, this one, and we will check all those to see what they mean. So we have added a few criteria. So this criteria, for instance, is one of them was the non-astigmatic validity. So the fact that the two defoci are not the same means that at a certain frequency, said differently, most algorithms, most 3D reconstruction algorithms assume that the data is non-astigmatic. This assumption is valid up to this frequency here. So this assumption is valid up to 0.34 angstroms. For instance, for this one, this is the worst case. It is only valid up to 3 angstroms. But 3 angstroms is well beyond the Nyquist frequency. So we don't care if this image, there are some errors beyond 3 angstroms, because we will never reach 3 angstroms. Then this idea of astigmatism can also be verified through the ratio of the first zero. So the first zero of the CTF, that is this black ring here. So the first time the power spectrum drops to 0, and or the CTF drops to 0, and we can check which is the ratio between two orthogonal directions. So these two orthogonal directions, the ratio between the first 0 is also very close to 1. So that means that these images are not astigmatic. We can also take the power spectrum, rotate it by 90 degrees, and if there is no astigmatism, then the two images should correlate pretty well. In this case, they correlate like 0.94. So we can verify for the worst correlating image. For instance, this one is the worst correlating. The worst correlating image certainly seems to be a little bit astigmatic, so it is not a good image for processing. And otherwise, all the rest of correlations are pretty high. Also, this correlation is useful to verify whether there are ice contamination, because the ice has some spots that when you turn them 90 degrees they don't correlate well. And also we have what was the fitting value by the algorithm. So this theoretical model is fitted to the experimental data by minimizing some error or maximizing the correlation. So here we have the fitting value. The higher the fitting value, the better the fitting has been done. Okay, so again, we would take all these micrographs that are the ones we like. This is a rejection suggested by the algorithm, but you may reject some other micrographs, and you would create a new set of micrographs with those that you like. We did that already, and this is this box here that we have called good CTFs, and as you can see, it has 14 micrographs. We rejected just one. Then we also have we have done two estimations of the defocus, one by CTF-Find, another one by XMIN. So we can compute what is the discrepancy between the two. So if we look at this form, what we see is we have two CTF estimations, and we will compare the two. So the analyzed results here tell us these two datasets are consistent up to 7 angstroms. This is a Nyquist frequency, so this is good. So the both algorithms are consistent up to this point, and we can also compute the discrepancy in astigmatism. So an astigmatism of 500 angstroms is relatively good, particularly because this defocus is relatively high. So this 500 angstroms in this high defocus is a very small percentage of it. So here we would also be able to reject micrographs for which the two CTF algorithms don't agree on the defocus. So at this point, what we would have is a set of micrographs that we have corrected for the beam-induced movement globally. We have also corrected locally. We have verified that the movie gain was correctly applied. Then we have inverted the contrast to have white particles over black background. We have estimated the CTF, and we have kept those micrographs for which we are happy with the CTF. So with this we finish this video, and in the next video tutorial we will go to the particle picking part and see how to extract particles from these micrographs.